Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discuss about the number of PMR signals. Number of PMR signals depend upon the number of types of proton present in the given organic compound. That's the so simple. So find out a number of types of proton or number of sets of proton or number of kinds of proton is nothing but as the same. And whatever the number of sets of protons are present, it will produce the number of PMR signal or NMR signal. And by using that formula, we have calculated, we have discussed so many examples by considering that concept. So now today what we are going to discuss is this one: position of PMR signals, shielding and de-shielding. What do you mean by the shielding and what do you mean by the de-shielding? Position of the PMR signals, position, exact position. What will be the exact position of, suppose, as a methyl group? Methyl group, as we know that it is present different, if it has a different environment, the chemical shifts are the different, that depend upon the environment, what kind of the environment around it, and that will produce the position of that signal will be the different if the same proton, suppose as a methylene group, let us see here CH2, CH2. If these CH2, CH2 are in a same environment, the position of that signal or the chemical shift will be the same. But if even though it is a CH2, but it is attached to but it has a neighbor are different, means its chemical environment is a different, they are the chemically non-equivalent, then definitely they have different chemical, the position of the signals would be different due to the environment around it. And sometimes the chemical shift is generally shift, sometimes is higher or sometimes is lower, depending upon the surrounding, what type of the groups are present over there, what type of the effects are present, depending upon the position are slightly changing than the normal position, and therefore it is termed as shielding and the de-shielding. Suppose let us see proton, some of the group like as electron withdrawing group, like as a halogen atom, and as we know that halogen atom are more electronegative in nature, they have a tendency to pull the electron toward itself. Ultimately, that proton would be the de-shielded. And if the electron density is go away from that proton, then that proton is termed as a de-shielded proton. And if there is a electron donating groups are present, generally electron donating means the electron releasing groups, they release the electron, and when they release the electron, electrons are surrounded that particular nucleus of the hydrogen atom, means that nucleus gets shielded, and that type of the proton is called as a shielded proton. So with this, let us see some of the example based upon other things where which we can see some of the point regarding that. later on. But now let us see shielding. We are discussing about the shielding and the de-shielding, where in all our discussion so far we have considered only the nucleus of hydrogen atom, that is a proton. Understood this? In all our discussion so far we have considered only the nucleus of hydrogen atom, that is a proton. However, such a bare or naked proton never exists. The proton is always associated with its electron involved in covalent bond formation with other atoms, carbon, nitrogen, oxygen, etc. Sc, HO, Hn, like this. Sc, then HO, then Hn, like this. This proton is never naked, never bare. It is always associated with some other electrons revolving around it. The proton therefore is always surrounded by bonding pair of electrons. Bonding pair of electron, and this bond is nothing but as a sharing of electron, like this. But this sharing of electron means bonding pair of electrons. The proton therefore is always surrounded by bonding pair of electron when an external magnetic field is applied to proton. The circulating bonding electron pair produce its own magnetic field known as diamagnetic field or induced magnetic field. Let us see here, I am going to show over here. Let us see, this is the nucleus of proton, and as we know that it is spinning along its axis, it is a spinning, and when it is a spinning, there is this type of the electrons are generally revolving or moving around it in a definite orbit. So like this, they are moving in the same direction. These are the electrons, circulating bonding electrons. This is known as a circulating bonding electrons. Circulating bonding electrons. Now is the induced magnetic field sigma H0. Here, like this. When this is the induced magnetic field on both the side, is the induced magnetic field which is represented over here like this, not this one, like that. So you can show over here this way. Induced magnetic field, this is a induced magnetic field. Induced magnetic field which is represented by sigma H0. H0, as we know that it is applied magnetic field, and sigma is a screening constant, and induced means particularly induced over there. Now when this arrow, as we know that it is nothing but as a H0. H0 means what? It is a applied magnetic field. It is nothing but as a applied magnetic field. It is a applied magnetic field which is represented by H0, this one. Applied magnetic field is 0. And now this figure depicted over here, shielding of the nucleus due to shielding of the nucleus due to induced magnetic field due to induced magnetic field. So here shielding of the nucleus due to induced magnetic field, this one is figure represented here. And now look at, this is a spinning nucleus of the proton, and around that these are circulating bonding electrons, this bonding, because that hydrogen may attach to carbon atom, it may attach heteroatom like oxygen, nitrogen, but this is a bonding pair, means number of electron, and they are revolving around it, and this is a when the external magnetic field is applied, that induced magnetic field is induced over here, and which is represented as a sigma H0. The induced magnetic field most of the time act in a direction opposite to the direction of the applied magnetic field. In some cases, these two magnetic fields act in the same direction. The magnitude of the induced magnetic field is given by sigma H0, where H0 known as shielding constant, and as the induced magnetic field is in opposite direction to the applied magnetic field, the magnetic field actually experienced by the nucleus H effective is less than H0 and is given by H effective. Now I am going to represent over here H effective. H effective is equal to H0. This is a H0 is a induced magnetic. This H0 is a applied magnetic field minus sigma H0 is a induced magnetic field is shown over here. The induced magnetic field does shield or protect the nucleus from the external magnetic field to some extent, and this phenomenon is known as shielding. Thus, even if we apply magnetic field H0, the nucleus will not get excited, since the magnetic field experienced by the nucleus is H effective and not H0, and therefore we will have to increase the magnitude of the external magnetic field so much that the effective magnitude field becomes equal to H0, means applied magnetic field. And if we apply a magnetic field H0 equal to 14,092 Gauss to a normal proton, the induced magnetic field sigma H0 is found to be sigma H0 is found to be 0.3 Gauss. and therefore the effective magnitude field is 14091.70, and therefore 14091.70 Gauss. And H effective is therefore H effective, you substitute value H effective is equal to H0 is how much? 14,092 minus is 14,091.70, and it comes around 0.3 Gauss. That's the answer. H effective is equal to this much. 92 minus 0.3 equals, so remaining is 14,092.70 Gauss. That is the answer, comes out over here. That is, even though we apply magnetic field of 14,092 Gauss, the field actually experienced by the nucleus is less than that is 40,091.17 Gauss, and excitation of the nucleus will not take place. In order that the nucleus should experience a field of 40,092 Gauss, that is H effective is equal to 40,092 Gauss, the applied magnetic field H0 should be increased, say to 14,092.30 Gauss, and thus due to diamagnetic shielding the absorption takes place at higher magnetic field. The signal is obtained at up field or high field. Any group that will increase electron density around the proton will shield the nucleus, and that proton will require higher applied magnetic field. That's the very important point which we are pointed out here. What is that? Let's see over here. We are discussing about the shielding and the de-shielding effect. Now here let us see here proton attached to this carbon atom. Now let us see one group over here, which is an electron donating group, which will shield that proton. Shielded proton. Here what is going to happen? Shielded proton. In a simple way, HC, now here is a Y, which is electron withdrawing group. So de-shielded proton. De-shielded proton. Now look at it. Now if you observe this structure, or if you observe here Y is the electron donating group. Ultimately this proton gets shielded. When proton gets shielded, the applied magnetic field must be as higher, and therefore that proton must be as a shielded. And de-shielded proton means what? That proton, the electron density goes away from that proton, and it means it gets deprotected, and that's the meaning of that de-shielding. And where the applied magnetic field is required is very less, and proton, the position of that proton will be there here. Logically, any group that will decrease the electron density around the proton, logically, any group that will decrease the electron density around the proton will decrease the shielding, that is cause de-shielding, and hence the absorption will take place at lower magnetic field. And thus an electron density around the proton increases, shielding increases, and absorption occurs at high field, and as the electron density around the proton decreases, de-shielding will increase and absorption occur at low field. Position of peaks. Now position of peaks. 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 Let's see over here. The shielding or de-shielding of proton, shielding or de-shielding of proton depends on the chemical environment of the proton. Shielding and de-shielding of proton depends upon the chemical environment of the proton. And proton which are in different chemical environment absorb at different magnetic field. Proton which are in identical chemical environment, will absorb at the same magnetic field. The PMR spectrum of this one, the first spectrum taken with this ethyl chloride, it is one of the simplest compound. The spectrum when text, it looks like this. One peak is around here, one is over here. So this is a peak. Here magnetic field H0. Here is a magnetic field is H0 represented over here, and here on y-axis there will be a absorbance. This is the peak observed due to the CH2, and this is the peak observed due to the CS, because these two protons are totally different in a chemical environment, and that's why they produce the two peaks or the two signals. This is a down field. This side is called as a down field. Down field, and this is known as a up field. Up field means high magnetic field required. Down field means is required as a less magnetic field. The PMR spectrum of ethyl chloride will therefore consist of two peaks, one corresponding to methylene proton and second corresponding to methyl protons, as they are in different chemical environment. The methylene proton will absorb at lower magnitude magnetic field due to electron withdrawing inductive effect of chlorine. That is, they are de-shielded as compared to methyl proton. The peak due to methyl proton will be upfield, and that due to CH2 proton will be downfield. This is the downfield and this is upfield. That's uric. And both the methylene proton are in same chemical environment and therefore absorb at same magnetic field. That is produce one peak. All the three methyl proton also produce one peak. The position of peak in PMR will therefore be depend on the chemical environment of the proton. Remember here, the position of the peak in PMR will therefore be depend on the chemical environment of the proton. Shielded proton have upfield peak and de-shielded proton have downfield peak. That is the discussion which we have discussed over here. So remember over here, shielded proton and the de-shielded proton, when electron donating groups are present, that proton ultimately get absorbed over there, and that the that is known as a down field, means the magnetic field required for this peak is higher as compared to that one. Here, look at here, methyl group, they are the chemically same, therefore you can call it as a proton. This you can call it as a 2 proton, means there are 2 kinds of proton present in the methyl chloride. Now, the methyl chloride has 2 types of proton, and therefore it will produce 2 sets of PMR signals, 2 sets of proton, 2 NMR signals. Now, which one is a shielded and which one is a de-shielded among these 2? Because they are totally in a different chemical environment, but this methylene group further attached to the chlorine atom, and as we know that chlorine atom is a more electronegative in nature, it withdraws the electron from this proton. And when chlorine atom withdraw the electron, these proton get de-shielded. De-shielded means the chemical shift value is very high here, but they are in a down field. They are in a down field, and as compared to this, the effect, electron withdrawing group effect, is less over here, and therefore it is upfield, or the peak of this due to the methylene proton is observed at a upfield. So in this way we have discussed the meaning of shielding and de-shielding effect, how that proton gets shielded or de-shielded. So that description we have discussed over here. In the next lecture, I think we are going to discuss about the measurement of chemical shift. What do you mean by the chemical shift? What is the exact position of those proton? What is the scale? What are the definition of the chemical shift? How mathematically it is calculated, and all those things which we are going to discuss in our next lecture. I think with this, let us stop today here. Next point we will see in the next lecture. Thank you. Have a nice day.